Okay, so I'm going to record the walkthrough that we do here with the comparing simple harmonic motion to uniform circular motion sheet. And if you guys have questions, you can still stop me. I'll just answer them as we go. So to review what we figured out here from the energy analysis. So analyzing the relationship between kinetic and elastic potential energy for a spring mass system. I guess the way I would summarize it is to say that the total energy of the system would be the kinetic energy of the mass. So the mass is moving at different rates at different points, plus the energy stored in the spring. And what we assume is if there's no energy dissipated, that total is constant throughout. Just to review each of these, the formula for kinetic energy is 1/2 mv squared. And for a spring, it's 1/2 kx squared, where k is the spring constant, x is how much the spring is compressed or stretched. So kind of the two important points for a spring mass system, if we imagine it kind of oscillating back and forth. When it reaches the maximum extension and compression, it's not moving. So when the spring mass system is here or here, you've only got energy stored in the spring. When it reaches the equilibrium position right in the middle, the energy is all kinetic because the spring isn't storing any energy if it's not stretched or compressed. So we kind of worked through that. And it's an interplay between those two energy amounts to get to your total. Okay, so really, I guess both of those objectives are kind of addressed by that summary. One important thing that we did prove is that if you have a ratio of the amplitude over the maximum velocity, that ends up equaling the square root of the ratio of the mass attached to the spring mass system over the spring constant. Okay, so I'm not going to walk through that proof here, but we did show that yesterday using the energy relationships. We're going to use that going forward today, so that although it's not in itself a really, really useful equation, we're going to use it to derive something today. Okay. So the rest of these objectives go with the sheet that we're going to work through today using that online simulation. So I will close that. Okay, so we're going to take a look at this simulation in motion in a second. And just to review for our own purposes how we defined angular velocity before. So if something's moving in a circular path, how did we define the omega term? Okay, and it's really the same as velocity in a linear sense. It's change in position over change in time. But for something moving in rotational motion, we call the position theta, so the radian position over delta t. Okay, so if I wanted to define an angular speed for this rotating object, let me bump it over to the simulation. So let's think of it as circular motion for a moment. If I wanted to know its angular speed, let's just time how long it takes to go around the circle once, right? So it would go 2 pi radians in a certain amount of time, right? Its change in radian position would be, for one rotation, 2 pi radians per unit time. Okay. So one way I could define it would be 2 pi over the period. right? The period would be how long it takes to do one cycle of motion. So we can do that same thing for a spring, in a sense. It's angular frequency, we call it. So we won't call it angular speed because it's not really an object moving in a circular path. We call it angular frequency, but we measure it in the same way. We would time how long it takes to go through one cycle. So maybe from now until now. However long that is the period. And one cycle is 2 pi radians. So we're going to use that same idea to define simple harmonic motion. Okay, so one thing we can note, another way to think about this would be it's 2 pi times 1 over t. That's equivalent, right? The definition of frequency is the inverse of the period. So another way we could represent this whole quantity is 2 pi times the frequency. Again, when we talk about frequency, we're talking about the number of seconds per cycle rather than the number of, the number of cycles per second rather than seconds per cycle. Period is how many seconds you have in one cycle. Frequency is how many cycles you have in 1 second. So they're just the inverse of one another. So we kind of have two ways to determine or define this omega term, the angular frequency. It's 2 pi times the frequency, or 2 pi over the period. Okay. So one thing we can note, and we kind of already looked at this, if we view the ball edge on, it's also representing simple harmonic motion in a sense. Okay? So we can describe simple harmonic motion in angular terms. Rather than calling it angular speed or angular velocity, we call it angular frequency, as it says here, to distinguish it from its rotational meaning. So the definition is the same. Again, we've already written it, but this quantity for simple harmonic motion is 2 pi radians over the period, big T, how long it takes to go through one cycle, or equivalently 2 pi times the frequency. Okay. Now this term did show up in our initial investigation. Remember, our general equation from logger pro looked something like position equals amplitude times sine some coefficient b times t. Okay? This b term is what we're talking about here. The standard way of talking about it in physics for simple harmonic motion is omega, its angular frequency. So we could also equivalently write it as a sine omega t. Okay? Knowing that omega, the value of omega, is 2 pi over the period, or 2 pi times the frequency. Okay? And all of these will be given equations going forward. So when you take your quiz, these are provided. For the Edmodo quiz, it's just linked to the quiz itself. So these are not things that you need to memorize, but you do need to know kind of where it's all coming from and how you might apply them. Okay. Okay, so we've established kind of the meaning of this angular frequency, this omega term. It's the same as the B term that you found in the investigation. Any questions or clarification needed? Okay, so let's flip to the back of the sheet. So let's think about, again, circular motion. And what we want to do is think about how we might calculate the speed of the object moving in circular motion, the tangential velocity, so how fast it's moving, not in a radian sense, but in like a meters per second sense. The question we need to ask is, how do you normally calculate speed, right? It's just how far something goes per unit time. So if I jump back to the simulation and take it to the circular sense, again, let's look at one cycle. So if it goes around the circle once, the distance it travels is the circumference, right? The time it takes would be a period, right? How long it takes to do that one cycle. So if we want to calculate the speed of the object, so I'll call it v tan. So the tangential speed, in other words, how fast is this object going at any given instant in a linear sense? I could calculate it if I took the circumference of the circle and divided it by the period, right? So this c represents circumference. And we calculate that as 2 pi r, right? 2 pi r is the formula for circumference divided by the period. Okay, so this next step, it's going to get a little bit tricky, and we're going to use the moving simulation to do this. What we're going to look at, again, this ball, this object in simple harmonic motion is moving back and forth. Okay, we want to think about what's going on when it reaches its maximum velocity right at the middle point. So if it's moving back this way, it has a velocity in that direction. It's going to slow down, come to a stop, and then accelerate back through that point. On the way back, it's going to be moving again with that maximum velocity in the opposite direction. I want to think about how that relates to this tangential velocity that we just were talking about. Okay? So let's look at it. Let me put the velocity vector on first of all. I'm going to pause it. And this is actually giving me components. So I've got my tangential velocity, which at any point would have a component that's leftward and in the up-down direction. If I go through it kind of stepwise, when it's moving that way, all of the velocity is downward. When I get to that point, and this point, notice all of the velocity is to the left in this case. Down here it was to the right because it's tangent to the circle. Now again, if I slide this down and just play it, notice that the velocity in a simple harmonic motion sense is greatest right when you pass the equilibrium point. So let me step through that again. The velocity goes to 0 for an instant when it's turning around, and then it gets faster and faster as it is pulled by that spring to a maximum. Okay, goes to 0, gets as large as it will be as it passes that equilibrium point. So the tie between this picture and this picture would be that this tangential velocity that we calculate here is the Vmax. Okay, it's the maximum speed of the object as it comes through. So this, oops, is equivalent to that. It's the same as that, just in the opposite direction. So as it comes back through that equilibrium point, it's the same Vmax, opposite direction. Does that make sense? Can you visualize that? Okay. So for simple harmonic motion, what we can say is Vmax, because it's one and the same as the tangential velocity from the circular motion sense, should equal 2 pi r. But let's think about this. When this was in a circular sense, the radius was this length, right? if this is a spring mass system oscillating back and forth, how else would we define that R? Isn't it the amplitude, right? Maximum displacement from the equilibrium point. So instead of saying 2 pi r, let's call it 2 pi a, the amplitude, because we want to put this in terms of simple harmonic motion. It still gets divided by the period, and the period is, again, just how long it takes to go through one cycle. Okay, so now we're shifting from the circular sense of motion to the simple harmonic sense. So we're putting it in terms of, maybe a spring mass system oscillating back and forth. Okay. Now, if I wanted to solve this in terms of period, right? So if I do some algebra on this, different ways to do it. Let's just multiply both sides by t to get that out of the denominator. And then I want to isolate this t, so divide by V max. Okay, so after all that's done, what I'm saying is the period for simple harmonic motion should equal 2 pi times A over V max. Okay. So now I'm putting it in terms of quantities that you might measure for something in simple harmonic motion. We're not even really talking about circular motion anymore. We can just isolate it in those sorts of terms that describe this thing oscillating back and forth in simple harmonic motion. Okay, so here's why I took some time to review what we did yesterday. We proved yesterday from the energy analysis that this was true. The amplitude over Vmax for a spring mass system will equal the square root of m, the mass attached to the spring, over the spring constant k. Okay. Look at what I have here and here. Same thing. So I can make a substitution, right? I can substitute this into this equation. Let's do that. So what I end up with, I'm just taking this period equals 2 pi times my substituted value here for A over V max, square root of m over k. Okay, so I kind of did the next step, but that's really kind of our final equation. So I can calculate the period of a spring mass system if I know its mass, so how much mass you're hanging on the end of the spring mass system, and I know the spring constant. And if you think back to the results from your lab, those were the only two changes that changed the period of motion. So if I took a spring mass system like the one from the lab, so if I hang a mass from a spring, the first trial, I just bumped it up a little bit and dropped it, so its amplitude was relatively small. In the second trial, I disturbed it a little bit more, so I let it swing between a larger amplitude. And if you remember the results from the lab, that didn't change the period. Okay? This is really kind of the proof of that the period is only dictated by mass hanging from the spring and the spring constant. Okay? If I increase the mass, I'm going to increase the period. If I increase the spring constant, so make it a stiffer spring, I actually decrease the period. Okay? The way I rationalize this kind of qualitatively is if I add mass to my spring mass system, I'm adding inertia, right? So it's going to take it longer to get through its cycle of motion because it has more inertia. The spring can only exert so much force. If I increase the spring constant, I'm putting a spring on there that can apply more force, so it's able to move the mass through its motion more quickly. Okay. So this equation, it's really a specialized equation. It's going to be a given equation from here on out. Its usefulness is if I gave you a certain mass and a certain spring, you could calculate how long it takes to go through one cycle of motion. It actually only ends up being tied to the mass and the spring constant. Okay? All right. So that's a lot of work to get to this equation, but I think it's always useful to look through it conceptually. Hopefully that helps you also understand some of the concepts a little bit better in linking simple harmonic motion to circular motion.